خاتم الأنبياء والمرسلين نبينا محمد وعلى آله وصحبه أجمعين. This is section 7.2 and it is about sampling distribution of the sample mean. So if you want, you can write here sampling distribution of X bar. Section 7.1 introduced the concept of sampling error. If you remember, the sampling error is X bar, the sampling error of the mean is X bar minus mu, okay? A random sample selected from a population will not perfectly match the population. Of course, if you choose a sample, the mean of the sample will be different than the mean of the population. So the sample statistic likely will not equal the population parameter. There is always a difference between X bar and mu. If this difference arises because the random sample is not a perfect representation of the population, it's called sampling error. So the sampling error is X bar minus mu. In business applications, decision makers select a single random sample from a population. They compute a sample measure, like what? Like the mean, like X bar, for example, and use it to make decisions about the entire population. This is very important now, and we will study this in chapter 8. Decision makers select a single random sample, choose a sample, and then they compute a measure, say X bar, and then they use X bar to make decision about mu, about the mean of the population. All right. For example, Nielsen Media Research takes a single random sample of television viewers to determine the percentage of the population who are watching a particular program during a particular week. So they take a sample and they use the information from this sample, the percentage of the people watching in the sample. They use this information to get or to determine the percentage of the population. This is what we call inferential statistic, using information from the sample to determine information about population. Of course, the sample selected is only one of many possible samples. If they select another sample, it will be different. That could have been selected from the same population. So for each sample, there is a sampling error. For each sample, there is an X bar. And X bar minus mu will be different for each sample. So the sampling error will differ depending on which sample is selected. If in theory you were to select all possible random samples, and this is what we need to discuss in this chapter, if you were to select all possible random samples of a given size, say n equals 5, 6, 7, and compute the sample means for each one. So we choose all possible samples and we select X, but we compute X bar for each sample. These X bars, these means would vary, of course, above and below the true population mean. Some of them would be greater than mu, some of them would be less than mu, okay? If we graph these values as a histogram, the graph would be the sampling distribution. So what is the sampling distribution? It is the distribution of X bar, and you can draw a histogram for that distribution. And this is what we need to study in this chapter. So what is the sampling distribution? It is the distribution of all possible values of a statistic. A statistic like what? Like X bar. For a given sample size, n equals whatever, 7, 10, 8, that has been randomly selected from a population. Please look carefully now to this example. 62 students took a business statistics midterm exam. The scores below reflect the population of interest. So our population of interest here consists of 62 students. This is capital N, the population size. The population size is 62. And here you see the scores, okay, of the midterm exam. Of these 62 students, the lowest is 29, the highest is 100. These are the scores of the population of students, okay. If we need to find the population mean, what is the population mean? It's the mu. We add all of these scores, the 62, and divide by 62, we find that the population mean is 71.43. Also, we can compute or calculate the population standard deviation using the formula we studied before, and the answer would be 16.8. So this is the standard deviation of the scores of this population, and this is also the mean, the population mean. All right. Now, let us have a graph of the population distribution. Okay, this distribution, the population distribution, if you of course choose classes, if you select classes, say for example like here 5 classes, if you divide the population into 5 classes under 60 from 60 to 69, okay, and draw the histogram, this would be the histogram of the population. All right, you have the mu, the population mean, it is here in the middle, and this is the standard deviation. Now look to this distribution. Is this a normal distribution? If you look to this distribution, it is not normal distribution. Remember, the graph of the normal distribution is like this. This is not normal. Under 60 is higher. It should be like this, like here. So this is not a normal distribution. All right. So the population has the distribution of the population is not normal. All right. Now let us start selecting samples of size n equals 5 from this population. Let us select 5 random samples of size 5 from this population. And these are the answers. We selected, for example, in sample 1, we have these 5 scores, sample 2, these 5 scores, and so on. We have 5 samples. Now, what do we need to find? X bar. Let us find X bar, the mean of each sample. Here we have different X bars. For each sample, you have X bar. And you can find the sampling error, which is X bar minus mu. We know that mu is 71.43. We calculated mu. So X bar minus 71.43, you will get these sampling errors. Look here, the error is 1.37. Look to this error, very huge error, 16.63. Look to this error, very small error. All right. So for each sample, there is an X bar and there is a sampling error. All right. Now, what if we choose 200 samples? By the way, how many samples of size 5 can you select from this population? If you remember, we answered this question last time. We have in the population 62 scores. To select 5 from 62, you can use this definition, 62C5 combination. If you use the calculator, it's really a huge number. 62C5, 6 million, 471,002. Imagine. So selecting 200 is very small number. Here we selected 200 random samples of size 5 and calculated X bar for each of these samples. And these are the first 5, here, the first 5 we select, and we continued. See, 200 samples. For each sample, this is the X bar. So this is only the X bar. And then we can find also the sampling error for each X bar, for each sample. So these are the sampling errors for the 200 samples. All right. Let us sketch the graph. We need, why are we doing this? We need to understand the distribution of X bar. The title of the section, sampling distribution of X bar. So these values of X bar, what would be the distribution of these values of X bar? So let us divide these values of X bar into classes. I have 200. Divide them into classes, say 9 classes, 3, 6, 9 classes. If you divide these values, the 200 values, into 9 classes and draw the histogram, this would be the histogram. This is the distribution of sample means of X bar for n equals 5. What do you see? I see a normal distribution. This is approximately normal distribution. So remember, the distribution of the population wasn't normal, while the distribution of X bar of size 5 is normal. Now, look here. These are X bar. These are the values of X bar. So X bar here is from 50 to 54. X bar here from 54 to 59. So these are the values of X bar. This is the distribution of X bar. This is the population mean, which we evaluated earlier. And this is the population standard deviation. So we have the sample mean, 200 sample means, and this is the distribution of these 200 sample means. Now, if we need to find the mean of this distribution, we will call it mu X bar. So what is this? This is the mean of the distribution of the sample means. The mean of the distribution of the sample means. You can add all the 200 means and divide by 200, you get 71.25. Look to this number and to this number. They are very close. And we have only 200 samples out of, as we have seen, 4 million. Now, if you take all the possible samples, here remember 6 million. If you take all the possible samples, you will find that mu X bar is always exactly equal to mu. So this is what you are going to find. Mu X bar would be always equal to mu, while sigma X bar is not equal to sigma. It's less than sigma. So sigma X bar would be found in this case 7.91. It's less than 16.8. It's not equal. It's not like the mean. Let us do this experiment again. Let us choose values or samples of size 10, not size 5. Okay, we will choose also 200 samples of size 10. If you choose 200 samples of size 10 and find all the X bars and do a distribution for these means, these X bars, you will find this histogram. It's a normal distribution. And you will find the mean of X bar is 71.32. It is even closer to mu. So when you increase the sample size, what happens? Mu X bar becomes closer to mu. And if you choose all the possible samples, you will always find the mu X bar equals to mu. And look to sigma X bar 5.12. For sample size 5, it was 7.91. For sample size 10, the standard deviation of the distribution of the sample mean is 5.12. This is less. So what would we conclude here? If we increase the sample size, we will have less variability in the distribution of the sample means. What are the other conclusions? The sampling error can be small or large, positive or negative, depends on the sample. The sampling error depends on the sample. The average of the sample means, what is this? What is the average of the sample means? This is a mu x bar, is approximately equal to the population mean. So this is our conclusion. Mu x bar is equal to mu. The variation in the sample means, this is sigma x bar, is less than sigma, variation of the population. They are not equal. The distribution of sample means is approximately normal. And this is very important conclusion. So these are the theorems we will have in this section. For any population, because our population in the example wasn't normal. So for any population, whether it's normal or not, the average value of all possible sample means, which is mu x bar, computed from all possible random samples of a given size from the population, equals the population mean. So mu x bar is equal to the population mean. So you have to differentiate between mu x bar and mu. Mu x bar is the average value of all possible sample means, but mu is the mean of the population. When the average of all possible values of the sample statistic equals the corresponding parameter, so when this happens, okay, whether for x bar or for not, we call that statistic, which is here x bar, is an unbiased estimator of the parameter. So what we conclude from here, x bar is an unbiased estimator of mu. This is very important because we will use in chapter 8 x bar to estimate mu, because x bar is an unbiased estimator of the parameter, because mu x bar equals mu. What is theorem 2? Theorem 2 will give you sigma x bar. We have seen that sigma x bar is less than sigma. But is there a relation between sigma x bar and sigma? Yes, this is the relation. Sigma x bar is sigma over square root of n. So if you go to here, for example, and try to find sigma x bar using that formula in the theorem, it's sigma over square root of n. Well, sigma is 16.8, and here we chose n of size 10, so find 16.8 over square root of 10. The answer is 5.31. So it's very close to this one. Remember, we did not take here all the samples. We have taken only 200. If you take all the samples, you will find sigma x bar equals to 5.31 exactly. Now, so the theorem that we can talk about now, the conclusion of all of this. If a population is normally distributed with mean mu and standard deviation sigma, then the sampling distribution of the sample mean x bar is also normally distributed with a mean mu x bar equals to mu, and the standard deviation sigma x bar equals sigma over square root of n. Now, sigma x bar, which is the population, the standard deviation of all the sample means, is also called the standard deviation of the sampling distribution. So sigma x bar is called the standard deviation of the sampling distribution, or it's also called the standard error of x bar. The standard error, not the sampling error. Sampling error, x bar minus mu. but the standard error of X bar is sigma X bar because it's the measure of the standard deviation of the potential sampling error. What can we conclude of all of this? What can the questions become be about this idea? Well, since the distribution of X bar is normal, so I can ask you about probability of X bar greater than or less than or between, and find X bar 0, find the value of X bar. The same questions we asked about X, any normal distribution in chapter 6. So X bar is a normal distribution. The distribution of X bar is normal, and we can ask the same questions. All right, if we want to find the probability of X bar greater than or less than, how would you change X bar to Z? Because usually in chapter 6, we change X to Z to find the probability. Remember in chapter 6, Z equals X minus mu over sigma. That for X. But what about X bar? X bar would be, Z here would be X bar minus mu of X bar over sigma of X bar. That's the usual formula we studied in chapter 6. But here, mu X bar is mu, and sigma X bar is not sigma. It is sigma over square root of n. So if you want to change X bar to Z, you use this formula. And once you change X bar to Z, you can evaluate the probability and you can find the probability easily. So let us just solve a question about this, two questions. If a population is known to be normally distributed and mu and sigma of the population, what will be the characteristics of the sampling distribution for X bar based on a random sample of size 25 selected from the population? He is asking only about the characteristics of the sampling distribution for X bar. According to this theorem, you just need to state this theorem, theorem 3. Okay, what are the characteristics? Well, the sampling, you can say that the sampling distribution of X bar is normal distribution with mu X bar equals to mu, which is 250, the population mean, and sigma X bar, this is the standard deviation of the sampling distribution of X bar. It is sigma over square root of n, so it is 40 over square root of 25 because n here is 25. This is the sample size. So that's mu, and this is sigma X bar of this distribution. The last example today, suppose that a population is known to be normally distributed. Mu is given, sigma is given. If a random sample of size 8 is selected, calculate the probability that the sample mean, what is the sample mean? That's X bar. So calculate the probability that X bar will exceed means will be more than 2,100. So this is the probability we need to find. This is X bar, remember, not a usual X, it is X bar. So how to find the probability of X bar? According to the theorem, the distribution of X bar is normally distributed. With mean, what is a mu? What is a mu X bar? Let us find mu X bar. It is equal to mu. It is equal to 2,000. So this is the mean of the distribution of X bar. What about the standard deviation of the distribution of X bar? It is the standard deviation of the population over square root of 8. So it is 230 over square root of 8. And this would be 230 over square root of 8. It's equal to 81.3173 if I take 4 decimals. So this is the standard deviation of the sampling distribution of X bar. How to find this probability? Since x prime, the distribution of x bar, sorry, is normal, so we just change this to z. So it would be probability that z is greater than. Now, how did you change x bar to z? We used this x bar minus mu over sigma over square root of n. So it would be 2100. Now change it to z. So subtract from 2000 mu over sigma x bar, which is 81.3173. Now calculate this by the calculator and approximate to 2 decimals, because the Z distribution is given in the table closer to 2 decimals. So Z is 1.23. Now find the probability that Z is 1.23 using the table of the normal distribution. To find this probability, this is what we studied in section 6.1. This is Z, this is 0, 1.23 is somewhere here, and we need this probability. This probability would be 0.5, all of the probability to the right of 0, minus this probability, which is given in the table, probability that Z is between 0 and 1.23. Find this probability from the table, subtract, and write the answer. This is the end of this lecture. Thank you very much. And if you have any questions, please ask.